what's that, chapter 3 or something? So, okay, we're ready to start. What we've been covering so far in the latest chapter has been the answer to this question: how can we properly distinguish Newtonian and non-Newtonian fluids? And so in the video, we saw a number of ways. We saw that if you put fluid into two tubes, you could detect shear thinning depending on how fast it flowed out of the tube. We saw him put it into a concentric device, and he saw some elasticity. We saw him pouring and pouring back and seeing elasticity, fluid memory, all kinds of things that were non-Newtonian. But as you can imagine, that's not very quantitative. We can't put any numbers on that. It's not a very well-defined test to go, well, let me see how much it springs back from one material to the next. So we're seeking ways of being quantitative. And as I said last time, we could just make up a bunch of ASTM tests and be quantitative that way. But that would be crude. That would be effective in some ways, and it is effective in industry for some types of calculation, some types of determinations. But we're trying for the gold standard. We're trying to be able to mathematically model a fluid in any circumstance. And so that's why we're forced to be more precise and quantitative in how we differentiate between Newtonian and non-Newtonian fluids. So what I talked about last time was breaking down fluid tests into two categories: shear and elongation. And I talked about one type of shear and one type of elongation. Today I'm going to talk about two other types of elongation, and then answer one of the questions I raised about the stress tensor. So just to get you back on the same page with me, we're now talking about a totally different mindset than what we were doing with Newtonian fluids. In fact, we're going to do the same thing we did with Newtonian fluids. We're going to do that with non-Newtonian fluids, meaning we're going to solve for velocity fields and stress fields. But we can't do that yet because we're missing the constitutive equation. So the constitutive equation for Newtonian fluids is that the stress, the extra stress, is given by del V plus del V transpose. A very simple equation. So this is Newtonian. And then for non-Newtonian, it's a big mystery. So this is what we're trying to do. We're trying to find this. So we're trying to find this equation for fluids that interest us. So in order to determine how things are not like this, not Newtonian, we need to make measurements. And that's what all of this business is about. And as I said, we are being very, very quantitative. So we're changing tactic. We're no longer solving for velocity fields. We're actually imposing a set velocity field. This is the velocity field that we are imposing. And we must design our devices to produce this. So these are the devices that have been designed to produce that flow. This one produces it in a straightforward fashion. And experimentally, these two are the most common of the ones shown here. These are the two most common geometries in which shear flow is produced. Shear flow is a sliding flow, and it is a flow in which the separation between two particles varies linearly with time. Okay? So I didn't go through this derivation. I don't think I will. It is in the book. But you can derive this final equation very simply from geometry for the distance that separates two particles that initially were separated by a distance L naught. So here they are initially separated by a distance L naught. And after some time t, they're separated by a distance L. And so if you double the time, you double the distance approximately at long times. The second flow is more complicated and harder to grasp. And this is going to be one of 3 elongational flows we'll talk about. I didn't say that last time. Why make things more complicated than they need be? But this one is called uniaxial elongational flow. And it's a flow that stretches along one axis. The axis is the 3 axis. And so there's compression along the 1 and the 2. So it's extending along the 3. It's a positive sign here. And it's compressive along the 2 and the 1. This flow is a stretching flow, and it occurs in things like, say, fiber spinning or flow out of an orifice. And experimentally in the lab, we produce it by devices that pull on polymer strands, or this is a suction device. I'll talk about this one a little bit later. Here again, we're pulling on a polymer strand. If we do the analysis on 2 particles that originally are separated by a distance L0 again, okay, here they are. Originally P1 and P2 are separated by a distance L0. If we do the analysis on this geometry, they separate exponentially. Okay? They separate exponentially. That analysis is also in the text. It's because the reason it comes out exponential is look at the velocity vectors. The velocity vectors are small and then larger and then larger. The velocity in the one direction depends on where you are in the one direction. That's exactly the kind of analysis that brings about the exponential. If you think about where the exponential comes from, you know that if you have dx over x equals dy, okay, you get y equals natural log of x, or e to the y equals x. Okay, you get the exponential when the changes are related to the position itself. Okay, and that's what's going on in this problem. The details are in the book. This is very different from the shear flow. In the shear flow, it was something times x2. But in the elongational flow, it's something times x1. So the farther in the one direction you go, the smaller the velocity gets. The farther in the 3 direction you go, the bigger the velocity gets. So it's an accelerating flow. These vectors are getting longer and longer in the 3 direction. And that acceleration leads to this separation that is exponential. So these are, in this flow, when you try to separate the particles, they must separate exponentially fast. And that's called a steady uniaxial elongation. Very different from in material science or in mechanical engineering, where they separate, they pull on a, let's say, a metal testing specimen, and they pull on it at a constant rate. Okay? Pulling on it at a constant rate is not deforming it in a constant uniaxial geometry. It's actually a different type of flow. This flow was picked to have a constant elongation rate. That's what this parameter is here. Epsilon dot is a constant rate of elongation. If at every point in space you're trying to elongate at the same rate, that's why it keeps, at every point in space you're trying to elongate at the same rate, not just right in the center of the specimen, and that requires you to be separating these 2 ends exponentially fast. So that's an interesting and complicated flow. Uniaxial elongational flow. Now, there are 2 more elongational flows that appear in the literature that I want to describe briefly here. And these are also flows that are characteristic, that are used to characterize non-Newtonian fluids. And one is called biaxial stretching, and the other is called planar elongation. Biaxial stretching looks exactly the same as uniaxial stretching. The only difference is the sign of the deformation. So this elongation rate was positive for uniaxial, meaning we were pulling the particles apart. And now we're going to be pushing them together and extending in two directions. So again, because epsilon dot has changed sign, this is now a negative quantity here. So this negative cancels this one. And it's stretching in the 1 and 2 directions and compressing in the 3. This would be something like bubble inflation. If you had a balloon and put a little grid on the balloon and then blew the balloon up, the little thin membrane that's the wall of the balloon is being stretched in 2 directions, and it's getting thinner in the 3rd. A controlled version of that would be to have a hole through which you're going to put air and a polymer film, and you can inflate it to a half cylinder, and that would be a way of measuring biaxial stretch. And I don't know if I have it here. And on the previous slide, we also saw a case of biaxial stretch here. Oops, too far back. This device is a biaxial stretching device. It starts with a sample of a certain size, and it compresses a little bit, which means that it extends it biaxially, and it compresses in the 3rd direction. So this flow, the idea behind these flows is they're just defined. It's up to the designer of the equipment to make them happen. And then we're going to define various things to measure for these flows. How do uniaxial and biaxial deformations compare? If we started with a cube of unit length or of length A, if you uniaxially deform it, it gets twice as long, and conservation of mass causes the sides to come inward by amount 1 over square root of 2. If you do biaxial stretching and double the length, then these 2 lengths here double, and the other direction, these 2 lengths double, and the other direction, because the volume must be conserved, reduces by 4. So it's qualitatively different type of a deformation. The third kind of deformation is one that's somewhat easier to produce, and that's why it's used. It's called planar elongational flow. And this is flow that only allows deformation in 2 directions. It stretches in the 3 and compresses in the 1. And this is something you might produce in this kind of a cross-channel flow, where this width direction, you don't allow deformation to take place. So you impinge 2 streams, one against the other, and then they come out like this. And so in this case, if you impose a biaxial extension in one direction, all of the volume change occurs in one of the 2 remaining directions, and the 3rd direction remains neutral. We can summarize these 3 flows all as one vector just for convenience. So all 3 of the elongational flows can be summarized like this. Elongational flow, the B is 0 and the deformation is positive. The biaxial, the B is 0 and the deformation is negative. And for the planar elongation, B is 1. This becomes a 2. This becomes a 0. And the deformation is positive. So this is just nomenclature here. Now, even as I'm telling you this, I'm feeling like I'm just listing a whole bunch of things that are not that interesting. So I'm struggling to make them a little bit more interesting. The problem with rheology, and as with so many topics in science, is you have to know so much before you can see how it all comes together. And we're in that difficulty right here. When we solved the Newtonian problems, we got pretty quickly into the issue of solving for the problems. It was very straightforward. We're trying now to move on to a non-Newtonian constitutive equation, and there's going to be, unfortunately, a lot of material to try to understand before it all makes sense. So what I've talked about so far are standard flows, and the idea being that we want to all agree, everybody in rheology wants to agree, how are we going to poke and prod at these materials in order to figure out their non-Newtonian character. So we've all agreed on these 4 flows. And frankly, we mostly use the 2, shear and uniaxial elongation. We mostly use the 2. So the one where the particles stretch linearly and the one where they, where they deform linearly and one where they stretch exponentially. Now, especially that elongational flow might seem more trouble than it's worth. It's a very complex flow. All this time we've been talking about fluids. We've been talking about shear flow. Why can't we just stick to shear flow? And the reason is in polymers in particular, it's the elongational behavior that dominates a lot of polymer processing. So if you try to separate 2 materials by just looking at their shear behavior, you can get 2 materials with identical shear behavior, and they don't mold up the same. They don't blow films the same. They don't produce the stresses the same. So we need a way to poke and prod them in the elongational sense. So why not just follow material science and stick them in an instron tensile tester and move the plates across following some ASTM standard? I'm going to discuss that now. Okay, why not a simple test like that? Seems like everybody does that already. It's very well accepted. Remember, our goal is to relate our measurements to the constitutive equation. The constitutive equation is an equation that relates stress and deformation. So the constitutive equation requires that we be able to say something about stress, and then over here there's going to be some function of velocity. So we are specifying the velocity. Let's say we specify the shear velocity vector, which is sigma dot. This is a special sigma, by the way. Maybe I didn't remember to point that out, but this is a special version of sigma that I've used in this formulation. Okay, so that's one velocity vector we're specifying, or we could specify the uniaxial one, which is epsilon dot, if I make these even constants, x3, x2, x1, epsilon dot over 2 negative, epsilon dot over 2 negative. Those I'm specifying, and now I want to measure. So this is what the instrument does, and now I want to measure the stress. So these are the experiments. Let's call them experiments that lead to the stress constitutive equation. Right? We're going to specify the right-hand side of the equation, put the sample in the instrument, and we're going to measure the stress. Now, how many components of stress are there? 1, 3, or 9? 9. So there are 9 components of stress. How many stresses do you measure in an instron testing instrument? 1. You can measure how much force it takes to move it apart, right? Stress is force per area. What area do you divide it by to get stress? Initial cross-section halfway in the middle, it's changing, right? The cross-section is shrinking in the center as I stretch it, right? So which one's the right one?
ASTM has you use the initial.
ASTM has you use the initial, that's correct. Is that the stress at all times? Is that the stress at steady state? It's just a choice, right? It's a very handy choice because you know it. You know the cross-section at the beginning. You don't even know the cross-section at the end, right? What's the cross-section at the end usually? It usually breaks, or it's 0, very close to 0.
Some of them will break, though.
Yeah, some just break. Some of the samples will just break. So you know what? It's not a steady test. The stress is constantly changing in that ASTM test. It's a standardized test, but it's not a steady test. And it's not measuring all the stresses. There are 9 components to stress. Well, that's too much, actually. Stress is symmetric. So if stress is symmetric, it's not really 9. Okay? This is really 6, right? The stress tensor is tau 11, tau 12, tau 13, tau 21. These two are equal. Tau 22, tau 23. These two are equal. Tau 31 is equal to tau 13. Tau 32 is equal to tau 23, and tau 33. So there's actually 6. Because tau is symmetric, we have 6 non-zero stress components to measure. As a function of position, and as a function of time for any experiment. Oh my gosh, that's a nightmare. Okay? We need to measure 6 stresses as a function of position. So everywhere in our flow, potentially the stress is different. That makes sense to us, right? The stress is different in different places. And as a function of time. Okay? So this is the dilemma of trying to make measurements that will lead to the stress constitutive equation. There are too many measurements to make to do it correctly. We can make ASTM-like tests. We cannot very easily make measurements that will lead to the constitutive equation. Well, but we don't need to make our lives needlessly complex. We can make it steady flow, and then we won't have to do it as a function of time. As a function of position is tricky. To make this simple, we can use a homogeneous flow. What does homogeneous flow mean? Homogeneous flow means the stress is everywhere the same, as not a function of position. Well, that's what we've just introduced to you. We've introduced to you 2 steady flows that are homogeneous. Stress not a function of time, not a function of position. Very good. Nice and simple. It's still not perfectly simple, though, because we have 6 non-zero stress components. So the other reason behind the design of these flows is we can use flows that are very symmetric. And reduce the number of stress components that we need to measure. And that's the answer to why we've picked these 2 flows that we're talking about. As I summarize on this slide, why have we chosen these flows? And the answer is because they're quite symmetric. And we can show that we can, in fact, for shear flow, we only need to measure 3 stress components. And also, actually, 3. There are 4 non-zero, but 2 are equal. And in the case of uniaxial elongation and biaxial stretching and planar elongation, only 3 again. So that cuts down the number of stress components we have to measure from 6 to 3. So we picked a steady flow, a homogeneous flow, and one that was very symmetric to simplify, 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 so we only have to make a limited number of measurements. Now, why wasn't this such a big deal for Newtonian fluids? Well, Newtonian fluids in simple shear have a single stress. That's why this has never bothered you before. It's a single shear stress. Newtonian fluids in elongational flow have 2 stresses as well, but it's a stress difference, and one of the two stresses was atmospheric pressure. So even for a stretching flow of a Newtonian fluid, there's a single measurement to make. The reason why this has never happened before is because you were never talking about non-Newtonian fluids before. And in these complex fluids, all the stresses are operative. None of them go away and are nice and simple. They're all there. And so we're forced to pick a situation that's as simple as possible. So let me show you a little bit about this calculation. Why does symmetry lead to a simpler stress tensor? Okay? So in general, as I was saying, the stress tensor is this 9-component quantity that we're now becoming more comfortable with. And it is symmetric due to conservation of angular momentum. There are some materials that don't have a symmetric stress tensor. Materials that have magnetic moments or conductive fluids that can have electrical moments if there's an electrical field, they can have a non-symmetric stress tensor. But we're not talking about them. All of our materials are symmetric, thank goodness. One thing that's not the most complicated case possible. Okay? So we can't, my question here, can we choose a flow in which there are fewer than 6? Yes, if we choose them symmetric. And here is shear flow. And now how is shear flow symmetric? Shear flow is symmetric in that if you pick a point in the center of the channel and choose a coordinate system, a Cartesian coordinate system, E1, E2, E3. If I consider, let's say, the stress at this point, P31, if I look at the point in this same coordinate system, so I went 3 units over, 1 unit up. If I go 3 units over and 1 unit down, P31, so this is, in this coordinate system, this is -3, -1, 0. These 2 points are symmetrically related. I can show this by considering 2 different coordinate systems. If I consider a coordinate system, the bar coordinate system, E1, E2, in this coordinate system, this point is called the same numerical value as this one. It's called 3, 1, 0. Now, what I'm going to do is I'm going to make an argument. I have this shear flow, and I'm looking at it in 2 different coordinate systems. Now, we've had a little bit of experience in the homework in transforming coordinate systems. We're going to use that experience. So this is one coordinate system, and this is the other. E1 bar, E2 bar. Remember, anything we do in fluid mechanics should be independent of coordinate system. So now I pick this point, which in the black coordinate system is the point 3, 1, 0. And I pick the 3, 1, 0 point in this coordinate system. So 3 over in the 1 direction and 1 up in the 2 direction. In the red coordinate system, this is the point 3, 1, 0. This is in the bar coordinate system. Now, first of all, let's visualize the flow. This is some shear flow. And if I put this line in the center, if I move this plate to the right and this plate to the left at the same amount, so let's say this is V and this is V, okay? All right, that's the same as, we usually draw the flow like this, all going like that. But if I put my 0 point in the center, it looks like a flow that goes to the right and goes to the left. I can produce this in a device by having walls that are on some sort of a big belt moving around. And the belt on the top is moving to the right and then circling around. And the belt on the bottom is moving to the left and then circling around. And I've produced a stationary shear flow. This point in the middle is stationary. Now, by looking at it and looking at the symmetry of the flow, we can tell that the velocity at this point 310 in the hat coordinate system, the velocity here, is the same as the velocity here. Okay, we can tell that they're the same, these two velocities. Okay, so that's what we're doing in this calculation. So here is my coordinate system, and here is the velocity at the top equal to the velocity at the bottom. Here's the coordinate system in the center. We can write the velocity function for this coordinate system, and we can write the velocity function in this coordinate system. Okay? So in general, when we write a velocity vector, it's independent of coordinate system. It's referring to the same velocity vector. When we write them specifically in these two coordinate systems, we get these two results. I'm about to write on the screen in a pen. Okay. If we write in the hat coordinate system, the velocity is equal to this velocity function, Vx. If we write it in the bar coordinate system, it's equal to this velocity function, which are the same. Okay? But they look very much the same, even though they're written in two different coordinate systems. So we've written the velocity vector in two different coordinate systems, but because of the particular choice of the coordinate system, and because the flow is very symmetric, they mathematically look very much the same. And if I put the equivalent symmetric point in, I'm going to get the same velocity. Okay? So that's what this says here. If we plug in the same number, okay, we will not be asking about the same point in space. So if I put in for x2, 1, I'll be talking about this point in space. If I put in for x2 bar 1, I'll be talking about this point in space. We will not be talking about the same point in space, but we will get the same number because the flow is symmetric. Okay? So that's what this means. The velocity component, any velocity component, written in the hat coordinate system, is equal to the velocity component written in the bar coordinate system. The stress component is a function of the velocity. So we always know this is the case, even if we don't know the constitutive equation. We know that the stress is a function of velocity. So that means that the stress component, numerically, the number, 16 Pascal, whatever the number is, will be the same for those 2 points. Okay. So in my experience of making this calculation, I know it all sounds very obvious up to this point. Okay. Now, so all I've argued so far is that the flow is very symmetric, and I have chosen two special coordinate systems, and they're the ones in which if you use the same dimensions, the same coordinates, you're going to get the same exact number for stress and velocity. Okay? Now I'm going to do something mathematical. That was the physics. That was the argument. We see the symmetry. Okay? Now I'll do something mathematical. Fine. I hope you believe me. But now I can do what we did in the homework. We can transform the coordinate systems. So we have these two coordinate systems. I'm going to have to redraw them. E1, E2, hat, and E1, E2, bar. Let's write them in terms of each other, just like in the homework problem when I asked you to write the stress tensor in two different coordinate systems. Let's write it here. E1 bar equals, what does that equal to in terms of the E1 bar? Right, negative E1 hat. E2 bar? Negative E2 hat. E3 bar? I'm taking them to be the same. Okay? So these are how the two coordinate systems are related. All right? And I can write the stress tensor in space. This stress tensor writes any point in space. And I can write tau ij ei ej for the stress tensor written in the hat coordinate system. And I can write the same stress tensor using different basis vectors, tau e I e j, but the barred ones. So in general, of course, I can keep writing coordinate systems. These are two particular ones that I've been talking about. But I know that I can just write tau in any coordinate system as long as I put a different coefficient out front, right? We expect different coefficients out front for different coordinate systems, but I can do it, okay? So this is just tau written generally. Now I'm going to do the calculation like we did it in the homework. This is tau 1, 1, E1, E1 bar plus tau 1, 2, E1, E2 bar plus tau 1, 3, E1, E3 bar plus tau 2, 1, E2, E1 bar plus tau 2, 2, these are all with bars on the top here, etc. E2, E2 plus. There are 9 of these terms. I can relate this back to the hat coordinate system using these. Everywhere I see a E1 bar, I can put this. Everywhere I see an E2 bar, I can substitute this. Okay, you see what I'm doing? It's exactly how we did the homework problem. Can you see what's going to happen? There's going to be some minus signs, right? Where are there going to be minus signs? Well, on the 1, 1 component? Why not?
Cancel out.
Right, because there's E1, E1, and they cancel. On the 1, 2?
Cancel out.
On the 1, 2, cancel again. On the 3, 1? Yes, there's going to be a minus sign. On the 2, 1? No. On the 2, 2? No. 2, 3? Yes. So what are they all having in common? The 3. Every time there's a component with a 3, there's like a mystery minus sign that's showing up. Okay? Fine. Let's write that down. 3, 3, except for the 3, 3. Correct, because that one will cancel. So if I write it in matrix form, I've written tau, okay? And I can write it in the regular coordinate system, tau 1, 1, tau 1, 2, tau 1, 3. No bars on the top. Tau 2, 1, tau 2, 2, tau 2, 3. Tau 3, 1, tau 3, 2, tau 3, 3. This is in the 1, 2, 3 coordinate system. All right? I wrote it in the 1 bar, 2 bar, 3 bar coordinate system, but then I transformed it, right, by doing all these substitutions. And you told me that in this position, I still have tau bar there, but there won't be any extra minus sign, right? This one, when I write it in this one, I originally wrote it in the bar coordinate system, but I've now changed it to the 1, 2, 3. And you said 2, 1, no minus sign. But you said 3, 1, there's going to be a minus sign there. Okay? So all I'm doing is collecting these terms. These are the barred, the ones with the bars on the top. And I'm putting them in the matrix form because that's just a little bit more organized. And there's these minus signs are going to appear. So this is tau 2, 1, no minus sign. Tau 2, 2, no minus sign. Tau 2, 3, there is a minus sign. Tau 3, 1, there is a minus sign. Tau 3, 2, there is a minus sign. Tau 3, 3, no minus sign. Now, we said previously, because of all that argument and hand waving I made, we said that tau ij equal tau bar ij because of the symmetry condition, okay? And yet when I equate these two, that does seem to be the case here. Tau 1, 1 equals tau 1, 1. It seems to be the case here. Tau 1, 2 equals the one with the bar. But what's happening here? Problem. If tau 1, 3 equals minus tau 1, 3 bar, and tau 1, 3 equals tau, this is 1, 3, not 3, 1. 1, 3. Yes. This should be 1, 2. Yeah. But no, it matters because what I know here is that the stress components are equal when they have the same subscripts. So these are meant to be equal, but here it says it's equal to its negative. The only number that's equal to its negative is 0. Okay? So everywhere these minus signs appear, I can prove by symmetry that those components must be 0. Tricky and nice. So here is that summary on the nice slides, printed out slides. We took the transformation of the matrices. We did the symmetric calculation, and we found that without putting the sample into the instrument, we already know that 4 of the stress components are 0. Okay, their history. That's the advantage of this choice of flow. We only need to measure 1 shear stress, not 2, 1 shear stress, and 3 normal stresses. Nice. If we do this same analysis for elongational flow, this flow has 3 axes of symmetry. I can rotate it 180 degrees, 180 degrees, 180 degrees, 3 ways. So that minus sign trick happens 3 times. All the shear stresses are 0 in elongational flow. There are no shear stresses in simple elongational flow. So it's a purely extensional flow. And there are only 3 non-zero stresses for that flow. So although these flows are problematic in some ways, they have tremendous advantages in others. And that's why they're worth the trouble. Because we can't make assumptions about the material. We need the material to be allowed to be anything. Because the whole point is to probe the material with these tests. Probe with the shear, probe with the elongation. The test must be designed to be simple, and this is what we've done. Now there's one more factor that impacts the calculation of stresses in our rheometric flows, and therefore that impact what measurements we actually make, and that's the incompressibility problem. So I'll say this once and then I'll say it again on Friday. So one final comment on measuring stress. When we measure stresses, there's this little problem of the isotropic stress on the diagonal. Okay? So for shear stresses, if we measure shear stresses, we have to be able to measure, let's say we put a sample in a device like this, and we move the top. If we can measure the amount of force it takes to move the top, we can measure the shear stress. So that's not too bad. When we want to measure a normal thrust, we can put a pressure transducer on the top of that device and measure a normal thrust. But it's not going to measure tau 1,1. It's going to measure pressure plus tau 1,1. Okay, because it's going to measure the total stress. Remember what the total stress tensor is? It's the stress at a point. The shear stresses are unaffected, but the normal stresses all have a pressure attached. Now, this wouldn't be a problem if we had some independent way of measuring pressure. So if, for instance, we were doing this measurement on an ideal gas, for an ideal gas, PV equals nRT, we could measure the number of moles, the temperature, and the volume, and we would know the pressure. We could subtract the pressure from what we get, and we would measure tau 11, and we would get 0, in shear flow. Because, in fact, this is not a stress that shows up in the shear flow of ideal gases. If we did a normal stress measurement on a complex, even then it wouldn't come, actually, because of the constitutive equation. It's not a problem for ideal gases because, actually, these stresses are 0 for ideal gases as well, which I can talk about later when we talk about the Newtonian constitutive equation for ideal gases. But for polymers, unfortunately, this pressure is very difficult to measure. So for ideal gases, this is a sketch of pressure varying, density and pressure variation for an ideal gas versus how pressure and density vary for an incompressible fluid. Totally no variation whatsoever. For real polymers, there is a slight variation, but you have to go up to 250 megapascals, that's a lot of pressure, to see even a 20% change in density for polymers. So that's why we mostly assume, actually almost universally assume, incompressible fluids. So going back to the total stress tensor, we do not have a way of independently measuring this pressure, so it always pollutes our answer. So as a result, we have a workaround for this, and it's called the normal stress differences, because we really don't need to know the absolute pressure. We just need to know the gradient. We just need stress differences, because that's what show up in the equation of motion in the microscopic momentum balance. So because we only need differences, it never bothers us that we don't know what the pressure is. We just need pressure differences and stress differences. So as a result, what we're going to talk about when we define what are called material functions is measurements of normal stress differences. So because the pressure is the same along the diagonal, pi 11 minus pi 22 is the same as tau 11 minus tau 22. And in simple shear flow, this is defined as the first normal stress difference. Pi 22 minus pi 33, there's a pressure in there, but it cancels, so that's equal to tau 22 minus tau 33, and that's called the second normal stress difference. So for our two standard flows, we have 3 quantities to measure in shear and 2 quantities to measure in uniaxial elongation. We measure the shear stress, first normal stress difference, and second normal stress difference. And in elongational flow, we measure tau 33 minus tau 11, which does not have a name, and tau 22 minus tau 11. So we've managed to reduce the number of variables that we needed from 9. We had to do 9 measurements of stress in order to completely make a measurement on a flow. But by choosing a steady flow that's homogeneous and that is highly symmetric, we've reduced it from 9 quantities to 3 for shear and 2 for uniaxial elongation. So I'll talk on Friday a little bit about the kinds of effects that are due to these normal stresses. And then we're going to move on. We'll do some examples, and then we'll move on to the next step, which is taking these stress quantities and doing our version of the ASTM. I'm going to define for you standard definitions, standard functions that are used as a shorthand in rheology for reporting to other people what have you measured, what have you observed for a given material under a given set of circumstances. So just like in ASTM, you have to specify shear flow. That's one part of the specification, but you have to specify how exactly do you move this top plate. You can move it at a steady constant rate. You can move it and stop it. You can not move it and start moving it. You can do it back and forth. You can do all kinds of things. And those are called the material functions. And that'll be then our next topic is what are the various material functions that are defined for describing non-Newtonian effects. Okay, so we'll do that on Friday. So on Friday, I'll give you back your homeworks, and we'll answer also any questions for the test if you have any on Friday.